Hello gamers. Another day, another scuffed Twitch stream, but that's just what we're here for. No, we're actually here for Polar things. Polar, my best friend Polar. A little R, a little theta. What more could you ask for, really? I think I could ask for nothing more from my best friend, polar coordinates. Oh god, physics is still up. No, we're not doing that right now. Please don't. Yeah, we're just gonna do some final integrals, final things to see if I can remember these formulas, because I have to memorize them. Oops, let me not run over my drawing board here. Hopefully, everything should work, and nothing should be broken. That's the goal. Don't know if that's gonna be the case, but sneak back. Okay. This is semi-comfortable. Alright, let's do a little... Oh, that's large. It's a good size. 5? Yeah, I like this color too. We can use this. It's like on the brink of being too small, but we like that. We like that. Alright, let me see. I think it's like page like 740, so we'll pop over there right now. Polar is actually kind of fun if apparently if you're taught about it in a way that is fun. So, you know, new lease on life from me. Polar coordinates, my best friend Polar coordinates. Well, maybe not best friend. Maybe not best friend, but certainly a better friend than before. So maybe my series of sequences log will turn around as well. Okay, so I'm gonna write the ones we're doing here. 9, 10, 17, 23, 24, 27, 29. That's a G. 29, 30, 45, 47. All right. Nice little set here. First page is 9. All right. Sketch the curve and find the area that it encloses. All right, that's not too bad, right? R equals 2 sine theta. So roughly, we know that this is going to be a... What is this going to be? Is this going to be a rose? It might be a rose. If it's going to be a rose, or is it going to be like a weird, like... I'll figure it out. Alright, so first off, we want to sketch it. Yeah, this is the big brain. This is the big brain move, chat. We want to sketch this thing in the XY plane. And yeah, I know you're like, what the fuck? This is polar. Don't sketch to the XY plane, but no. This is massive brain. Because we're going to use this to translate it to polar. Okay, so it's going to be 0 when pi equals 0. And then when pi equals... theta equals pi over 2. It's going to be 2. And it's going to be increasing. That's going to be a limation. Sorry, a cardioid. No, it's not. I lied. It might just be a circle. Then when it's pi, it's going to equal 0 again. It's just going to be a circle. Okay, slay. Let me do that. Okay. And then... Okay, that looks pretty good. But it goes around twice, is the thing, right? So we want to go from 0 to pi to get the area, which is cute. We love that. Let's just check real quick on Desmos to make sure that if we have r equals 2 sine theta, yep, it's a circle. Awesome. So cute. All right, so it goes around twice. Oh wait, I said I was going to draw the graph in space. I did not do that. I did it in my brain. Okay, it's fine. It's fine. We're normal. Okay, so now we have to remember the area formula, right? Everybody likes a little polar area formula. The polar area formula is 1/2 r squared d theta. Right? That is not the... Yeah, This is just area. I guess we're not doing arc lengths. Sorry, lied about that. Maybe we'll do some arcs after. Okay. Yeah, so 1/2 r squared d theta. From, you know, a to b, or alpha to beta, or whatever. So ours is going to be from 0 to pi 1/2 r squared, so that'll be times 4 sine squared theta d theta. Cute. So this goes away. We'll pull the 2 out here. We're going to get 2 from 0 to pi sine squared d theta. Not too bad. We can do power reduction on this. Before we do that, let's think in our brains if sine squared d theta is the derivative of anything. I don't think it is, so we're gonna do power reduction. I have done power reduction too much already in this course, when I was not supposed to, but... So this will be, since it's sine, it'll be 2. We'll just do this. 0 to pi. 1 minus cos 2 theta over 2 d theta. And this is so beautiful, chat. Like, it's really gorgeous. I don't know why I'm using arrows. These can be equal signs. So we're gonna get 2 times, and look at this. Here, we'll do like a really big bracket. That's a really large bracket, whatever. 1/2 d theta minus, well, we can actually pull the 1/2 out as well. Oh wait, actually, watch this. Watch this little trick here. 1/2, bam, get rid of them. Pi d theta minus cos 2 theta d theta. Look at that. Woohoo, this is turning out pretty good, eh? Okay. So this will be theta, so pi minus 0, so that's pi. I mean, I guess I can just do this, right? That's maybe a little bit easier. And then for cosine of 2 theta, well, if we're deriving that, that would be sine, right? Sine 2 theta. But this would be sine 2 theta times 2, so we need to do over 2. So sine 2 theta over 2 from 0 to pi. And then we'll get this to be equal to pi minus, at pi, this would be sine of 2 pi, which is 0, minus, wait. Wait. This is a little stupid, but like, for integral du USA for limits. Oh, this is not gonna give me the answer. Yes, this is always that is cool. I hope I just didn't quit my program. No, we're fine. So it's, yeah, sine of 2 pi over 2 is going to be 0. The sine of 2 pi is 0. And then sine of 0 is also going to be 0. So it's just going to equal pi. So pi, and then our, like, you know, whatever, you know, area, right, that it encloses. Let's see if we got that right, chat, shall we? That seems like maybe it's a little too nice. Although these things usually turn out to be honestly pretty nice. Like, nicer than you'd expect, I guess. So I'm gonna just pop this PDF I've open again, and then we're gonna go to the answers. Oh, hell yeah. Physics problem? Okay, a dog sees a flower pot sail up and then back down past a window 1.1 meter high. If the total time the pot is in sight is 0.54 seconds, find the height above the top of the window to which the pot rises. Okay. This question is hard to picture. Okay, let's draw it out. Sometimes when it's confusing as hell, yeah, it can be pretty confusing. Okay, let's start with the easy part. Let's draw a little doggy. Okay, so there's a dog, right? And the dog is at a window. By the way, the answer is 0. Okay, let's not worry about the answer right now. Let's just like worry about breaking down the question, right? So the dog is like sitting in a window. It's like sitting on a little, maybe he's sitting on like a little chair. He's having fun. He's watching the window. And he's like, oh, what's out the window today? And so he's gonna see a flower pot come up here. And it says it's gonna sail past the window. It looks like a cow. Damn. If there were little horns, then it would be a cow. This is just a little doggy, right? So it's gonna sail past the window. We know that, and then it's gonna come back down, right? So we know, because we know that it goes. We're gonna assume that it also goes down past this window. Right. So we know that. Good drawing though. Yeah, it's all right. It doesn't really have to be good. You just have to kind of figure it out, right? So we know that the flower pot is going to pass by the window twice. Now, one of the things we kind of have to know about this is that it doesn't make any sense why the pot will go up and down. Well, if you throw something up in the air, right? Let's say you're like throwing a ball up in the air, like the ball's going to fall down on the ground, right? What this is saying is if this flower pot was this ball in this situation, the window would be like here. So it's gonna see this part. It's gonna see like this part of this parabola, right? So it's just gonna look like the pot is coming up and then going back down. So that's why it's kind of a little bit hard, right? Because we don't know how far up this is going. We only know the time here. But one of the things we have to know is that the velocity, and this is just something that you kind of can visually recognize, and something that you'll learn when you are doing kinematics, is that at this point and at this point, the pot's velocity or the pot's speed is going to be the same. Or in this case, the ball. We'll just call it a ball, right? So when the ball is here and the ball is here, its speed is going to be the same, but in different directions, right? Because at this point it's going up, and at this point it's coming back down. So at this point in the parabola, because the parabola is symmetric, right? When you're throwing something right up in the air and it's coming back down, we're going to assume that they're throwing it directly up and then directly down. Like there's no angle in between, because they're not telling you like the pot was thrown at like a 25-degree angle past the window. It just comes straight back down, right? So what we can do is we know that the whole time the pot is in sight, which means that when it's flying up past here and when it's flying back down here is 0.54 seconds. We know that for one time the pot goes past, it's going to be 0.25 plus 0.02. Yeah. So for one trip, t is going to equal 0.27 seconds. And we know that the window, right, which is the distance that it's going, is going to be the distance that the window is long. The delta x for that 0.27 seconds is going to be 1.1 meters. Right? So now we're starting to get some good stuff here, because we can get velocity out of this, right? Or we can start to think about speed. We can start to think about the relationship between the stuff. Another thing we also know, right, is acceleration. Because when you're on Earth and you're doing anything, your acceleration is always going to be negative 9.8 meters per second squared. Because gravity is affecting something that's getting thrown or something that's standing there or whatever, right? So it's asking the height above the top of the window to which the pot rises. Now this is kind of tricky because, right, we don't know how far this pot has been going, right? We just know that it, at this point, oh, it's really tricky as a non-native English speaker, especially. Oh yeah, 100%. My physics professor or my physics teacher in high school, like actually, because he taught an AP class, and the AP has some very specific language, right? That says, like, for example, like evaluate or like sketch versus draw versus graph. He actually made sure to like specifically talk about like what all those different things meant, because he knew that he was teaching students who, you know, maybe didn't have English as their first language. So it's definitely something that's really hard in physics. Oh, let me see the question again. Let me scroll up real quick. So what I think he would do here is, well, let's take a look at our equations, right? Let me just go and grab like an image of the equations, because that's always where it's a good thing to start, right? I just Google literally 3 physics equations because they'll always come up as the kinematics equations. You got x equals initial velocity plus 1/2 9.8 times 0.7, which is initial velocity is 2.751. So that's right, I'm sure. But what we have to think about is, right, what do we want to find? We want to find the height above the window, right? And this is where, like, when I'm doing this problem, I don't actually know the correct answer, like, right away. But we don't know how far the window is from, say, the ground or the starting point of this pot, right? So if we found the initial velocity of this pot at the bottom of the window, wait a second. Let me think about this. No, never mind. You're actually right. Then that's why we love working in pairs. No, so yeah. The initial velocity will be at this point, because this, we'll just say from here, like, okay, let me do this a little bit better. At this point, right at the sill of the window, the bottom of the window, t is going to equal 0, x will equal 0. And then we can find, what do we want to use? We can do this equation, right? So yeah, delta x 1.1 equals VO times 0.27 plus 1/2 times negative 9.8 times 0.27 squared. So you are 1000% on the right track. Good job. Let me pull out my calculator here, because we actually need this number. So it'll be, hey, no, just guessing is like all right, you know, it's intuition. Yeah. I plug it into the formula, so true. No, it's one of those things where, like, you also don't want to overthink it, you know. I tend to overthink things a lot, so, you know, take anything I say with a grain of salt until I, like, come around to the right answer. So 1.1 plus 0.5 times 9.8 times 0.27 times 0.27. And then this divided by 0.27 will be 5.25, which is a pretty good number. Which gives us a nice sign that we might be on the right track, right? If you get a nice number like something like this, like that's pretty dope. Okay, so now we have to do the second part, right? We want delta x. We want our second delta x. So the final velocity will be at the top of the window. Now that's where we're going to change things up a little bit, because we want how high above the window it goes, right? We want up here. So what we're going to do is, we know at the top of this thing, there's a point where the ball turns around, right? So we know, like, if you want to examine this in a calculus way, we know at the top of a parabola, the derivative is going to be 0, right? So in this case, that means that we know by intuition our velocity should be 0, because velocity is the derivative of position. But also we can think about it this way, right? Since velocity is a vector, velocity is positive, and to get velocity to go negative, there's going to be a point where it has to be 0 before it starts turning around. right? So yeah, at the top of the parabola, you know, when you're changing direction, you're always going to have a point where you have zero velocity. So what we want to do is we want to say, okay, our v initial is going to be 5.5 meters per second. Our v final is going to equal 0 meters per second, because we want to find the delta x, right? So delta x equals, we know our acceleration equals 9.8, negative 9.8, and we don't have a time, right? Because this is a, we don't know how long that's going to take. The dog does not see this part, right? The dog only sees in here. So now we have to look at our equations. We say, okay, which one doesn't have time? Because there's only one equation that doesn't have time. It's this equation. So we're going to use equation 4. Where did you get 5.25? Oh, I just solved this part out. This was the first equation that you gave, where we used this equation, equation 3, and we plugged in our delta x, which we had, we plugged in our time, which we had, our acceleration, and our time again. Oh, did I get the wrong answer? I could have gotten the wrong thing. Let me try again. 1.1 plus 0.5 times 9.8 times 0.27 times 0.27 divided by 0.27. Oh, I got 5.39. We can try and do it this way just in case, to make sure. We're gonna get v squared, we're gonna get delta x minus 1/2 a t squared over t, right? So let's make sure we're plugging in that, and I'm gonna put it in Desmos real quick, just because then I'll know that I will put it in correctly. Oh, did I close Desmos? So let's do this. 1.1 is our x, right? Minus 0.5 times negative 9.8 times 0.27 was our time, squared, 2.7, and then all of this divided by 0.27, which is, yeah, it's gonna be 5.39. I don't know why I got 2.5. 5.39. 5.397, but we'll just keep it at 5.39. So that's what I got after plugging. Here, we'll just put this over here. After double check. So, but yeah, we're getting this from this previous thing, right? Because essentially what we're saying is we want our, here, I'll use a different color. We want our initial velocity to be here and our final velocity to be up here when the ball is here, right? Because we know this is 0. And we already found this. 5 point something something, right? So we're gonna do that. And then we're gonna plug into this equation right here, equation 4. With all of this stuff, right? So this is equation 3, this is equation 4. So we'll do v squared, which is our vf, so 0 equals 5.39 squared plus 2 times negative 9.8 times delta x. So then we'll get, negative 5.39 squared over 2 times, over negative 2 times 9.8. It's going to equal delta x. And that's going to give us, here I will put this into Desmos just in case, negative 5.39 squared divided by negative 2 times 9.8. That's going to give us equals 1.4225 meters, right? So that's our delta x. Now, the last thing we have to think about, right, is where we're starting and where we're ending. Because the question specifically is asking how high above the window does the plant go? And we haven't really factored in the window, right? Because we're starting at the bottom of the window and we're going all the way up to the top. So the last thing we have to do is take this 1.4225 and subtract the height of the window. So that's 1.1 meters, which will give us 0.38. 0.38225 meters. And you said the answer was 0.39? Okay, maybe we had a little rounding something somewhere, but it's close enough where I consider it a win. Is that good? Make sense? I can answer questions if there's a part where you don't understand. It's basically about knowing when to use each equation at what time. And then also trying to figure out, you know, the problem, if the problem is stupid. Sometimes they're really convoluted. I'm just gonna go check on the answers over here for my thing. I don't remember what page it is. Yeah, if you get like close enough, can you explain when do we use the fourth formula? Okay, so once we have our initial velocity, right? Because in my brain, some part of physics that is hard, I think, for a lot of people to get, that isn't really talked about, is kind of the Lego work of physics. Like, because when you're solving a problem like this and you're trying to say, okay, what are they giving me? They're giving me a time that this dog sees a plant, and they want me to say how high above the window it's going. Like, how do I get from point A to point B, right? Like, what pathways do you have to take to get from point A to point B? So the first one is sometimes easy because you can say, okay, they only give us these things in the problem, right? They're only giving us time. They're only giving us the height of the window, you know, delta X. I'm going to look at 3, and I know that we can get something out of that, right? We can get another variable we didn't know, which is the initial. Then it's a question of, so are we going to have 2 more steps or more steps, or are we going to have 1 step? And because we know that we're trying to find, it's a parabola, it's a free fall, right? Problem where there's a body in motion in the air, and we're not going to talk about air resistance. We're just going to use kinematics. We have to hinge like our solution of this problem on knowing that this velocity at the top is going to be 0. So the reason why we're using the fourth equation is because we have 2 velocities, and we're always going to know an acceleration for free fall problems, and we want to find delta X. The other reason you can see it is because we don't see a time. They don't give us a time in between these 2 things. If they gave us a time in between these 2 things, our options open up a little bit, right? Like, so we could use this one, we could use this one, or we could use this one. But if we have a time, if we have no time, we automatically know that we have to use this one, because this one is the only one that doesn't have time. The rocket problem is the toughest. Yeah, rocket problems can be really tricky, honestly. Although I will say the ones that I use the most, I don't use 2 a lot. 2 is the one that I don't use a lot. These 3, 1, 3, and 4 are like the kind of bread and butter. This one is if you don't know, if you have no distance, if they don't give you a distance. This one is if they don't give you information about velocity. Usually this one is used when you're starting at rest and you want to find a velocity. Or it's implied that you will be at rest at some point. So in this case, it's implied that we're going to be at rest. Well, sorry, that's not really true. In this case, it's implied that we're going to be at rest, you know, here. But most of the time that you're at rest, this is a really good formula because otherwise sometimes you have to solve. Like if you were given a delta X and you were given, you know, a VO that was like, let's say like 2 and an acceleration of, you know, negative 9.8 or whatever, then you have to solve like a quadratic for t, and usually in first year physics they don't make you do that. So usually that's if VO is 0. I'm gonna turn on the lights 1 second, but let me know if that makes sense. So yeah, it's really just like we look at what we have and then just see which of the formulas we can move on to the next step with that can give us a variable we don't have. out of the stuff we do have. Pretty crazy though, not gonna lie. Yeah, it's a little bit tricky to get used to. I did a bunch of these problems in my last VOD, actually. I think you might have been here for some of it, but that was all kinematics. So if you're confused about like kinematics or when to use those equations, if you wanted to like see me work out examples, then that might be a good thing to go and watch. I also can do some more later. I have some that are a little hard. It's a lot harder than calculus in my opinion. Well, yeah, because with calculus, right, like let's take something like polar coordinates. If you know what the arc length formula is, 1/2 r squared theta, or r squared d theta, and you can evaluate integrals, then you're gonna get this answer. But in physics, you have to be able to see the connection between 2 points. You have to be able to get to point A, from A to point B, but you can't just do it in one step. In pretty much every application of physics, you have to go here and here and here, and then you can finally come to B. And a lot of people, and there are a lot of different ways you can do it. You can go here, 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 and this way, I think the hardest part in physics is you have to understand and know how to set up the question. That as well. Knowing how to get a good picture is pretty hard. It's only easy if you can set it up and plug in the formula. Yeah, so true. I honestly forget, I think a lot of the time, like for me, the hardest part is seeing the pattern from one place to another part for a lot of things, for math as well. Because I had math subjects that, like for example, trigonometric substitution problems where it was like, oh, you have like crazy bananas, like 2-chunk polynomial times like another 4-chunk polynomial like over itself, like, and it's all supposed to like equal like sine theta. Like that was very hard for me because I couldn't see how to get from point A to point B. I wasn't comfortable enough with my like, sine squared plus cos squared equals 1 and stuff like that to like be able to see those patterns. But I also do tend to forget, I think, that some people have like problems visualizing problems, which is a really big part of physics. But it does get easier, I will say that. Once you do these, you start to kind of see the patterns in them with these, because a lot of these problems are the same problem, is the funny thing. They're just taking out different parts of them. They're only giving you certain information. So once you start to notice that and recognize how the 4 equations kind of work together, it does become a little easier, but it takes some time, I would say. But also, I will say, if you don't like kinematics, it is not all of physics. All of physics is not like kinematics, and a lot of people struggle with kinematics and then have a really easy time with energy or forces, because it just becomes a very different study, honestly. Kinematics is a lot about there's a lot of trust in kinematics, in the formulas. Yes, this is kinematics, like the motion of objects. But for example, when you're talking about, I think the next thing you probably will learn about is forces, right? When you're talking about an object that has, the force of gravity on it and a normal force that equals, here's a better example. If you have an object on a slope and it has the force of gravity on it, and it asks you like the magnitude of the normal force this way, this just becomes like a math problem about like what is this angle and then how to split up a vector. Ooh, another one. Yeah, I can do one. Let's see. Okay. A rocket is fired vertically. Okay, let's draw it. Let's draw it out. So we have a rocket. This doesn't really look like a rocket, but it's fine. So a rocket is fired vertically and ascends with a constant vertical acceleration. Okay, so we can't use, so our A is going to be, well, no, we can't use it, sorry, 20 meters per second squared. for for 1 minute, right? So t equals 1 minute. Basically, if you see any numbers, just write them down and what they equal. That's what I usually do. We'll put this in seconds, 60 seconds. Its fuel is then used and it continues as a free fall particle. What is the maximum altitude reached? Okay. So this is not too bad, actually. So we have to figure out a couple things, right? So we're trying to find delta x. We know that. We know that this one might be helpful to not draw a picture, but draw some graphs, right? So we know that this is accelerating for some time. We know that this stops accelerating at 60 seconds. And then it's gonna go for a bit and then, start going down, right? What is delta x here? That's what we're trying to figure out. We don't know what that is. That's the maximum altitude, right? We want to figure out how far does it go up. So we know we have a graph where it's accelerating and then it's gonna go up for some time and then it's gonna stop and then it's gonna go down for some time, right? Only max altitude. Yeah, that's what this is our max altitude equals what? So I do like to draw a little bit of a graph like this because it kind of helps me visualize this. So we know that the velocity is increasing, right, until 60 seconds, that it's going to be constant, 0, and then it's going to go away, right? It's going to decrease at a constant, and this is going to be negative 9.8 because that's our acceleration. And then for this, we're going to have an acceleration, and this is going to be a constant at 20 meters per second, right? Until t equals 60. And then it's going to be negative 9.8. Negative 9.8. If you haven't learned about position, like acceleration, velocity versus time graphs, these are just graphs that we use where we graph the whatever we want to graph, position, velocity, time on the y-axis and t on the x-axis, and then this can, I don't even know how to draw the acceleration graph. Well, yeah, it's a little silly because we know that's a constant acceleration, right? Both times. If there's a non-constant acceleration, they are going to just give you a formula. Why is it a square? Great question. This is because in physics, this kind of stuff doesn't happen in real life. We don't have a constant acceleration of 20 and then just magically get a constant acceleration of negative 9.8. So the way that we represent this is at 20, this graph is just gonna show that the acceleration just turns into negative 9.8 at this time. That's kind of, so these dotted lines are just there for not really any reason. You can kind of think it as a piecewise function, right? Where from 0 to 60, a equals 20, and then from 60 to however long we're going, a is going to equal negative 9.8, right? Oh, did somebody just follow? Oh, wait. I forgot to change my Twitch activity filter. Thank you for the follow, Albor. I hope you're enjoying a little physics, little polar coordinates. Oh, gravity? Yeah, because gravity will take over. But we're not thinking about that for the first part of the problem, right? Let's start doing some stuff now, right? So we know that, let's start with the easiest thing we know. When it's at max altitude, our velocity is going to be 0. So we know our velocity is going to be 0 at max altitude, right? Now, the thing that we're going to have to do beforehand is a little silly, right? Because what my first instinct is go, well, we know our v initial. It's going to start from rest, obviously. So we can just throw that puppy in there. We can just say v initial equals 0 and then start plugging things in. We're ready to go. But then what would we say our acceleration is? We could say our acceleration is a function of time, and then we could integrate it and shit, but that sucks, right? Like, we want to have a constant acceleration to be able to use those equations, if you have a non-constant acceleration, like let's say our a is equal to t squared or something, you cannot use those equations, and you have to use integrals, derivatives, etc. So what we're going to do instead is, similarly to how these graphs, you can kind of see they're split up into two parts, right? In this case, it's 3 for delta x, but this is wrong, actually. This would be like this. No function, can't use integral. Well, we can make up a function, right? You know, a equals 20 meters per second. And then you can integrate this and do stuff with it. But what I'm going to do instead is I'm going to split it up into, sorry, this should really not go past the ground. Use derivative to solve these type of questions in calculus. Yeah, it's very true. But what I'm going to do instead, because I don't really feel like differentiating and integrating, is I'm going to split this into two parts. The part where the acceleration is equal to 20 meters per second, and the part where the acceleration is equal to negative 9 meters per second squared. All right? Make sense? Not integration, not more. Well, if you're taking engineering physics, you will be integrating, but not like this. They will usually give you functions that are a little bit more annoying to integrate than just 20 meters per second. Because it's a constant acceleration. You don't really need to integrate with a constant acceleration, right? Because we can use our equations for that. So what we're going to do is we're going to say there are a couple parts to the journey, right? There's going to be the first part where we're accelerating. There's going to be the second part where we're no A, but still up. And there's going to be a third part where we are falling to the ground, right? Fall to ground, negative 9.8. Well, sorry, not no A, negative 9.8A. Negative 9.8A. So what we're first going to do is we're going to find how fast the rocket is going after its acceleration, right? So for this first stage, we want to find the velocity here, v equals question mark, and it does not equal 0. And then we're going to use this as our initial velocity for the second part. So for our first A, let's figure stuff out. So we know a couple things about A, right? We know that our rocket is going to start at rest, 0 meters per second. That's a lie. VI, write the correct thing. VO, VI, I'll use VO. We know our acceleration is 20 meters per second squared. We don't know our T. They're not going to give us a T. We don't know our delta X. They're not going to give us a delta X. Do we know anything else? I think the answer is no, but it doesn't... Wait, do we actually get any other information? We might need something else. Oh, for 1 minute. Omega lol. They do give us a time. I was about to say, they have to give us a time. Anyway, 1 minute, 60 seconds. So we're going to use equation 1, which is V, I'm going to use delta V. Delta V equals AT, right? How much V is changed is equal to the acceleration times the time. So that means our delta V is going to equal 20 times 60. Delta V equals 300 meters per second. So our VF at this point, V is going to equal 300 meters per second. You're thinking, wow, that's a lot. Well, it's a rocket, so that kind of makes sense. That is the one thing that's nice about physics, is we can kind of conceptualize if our ideas are right or not, right? If this was like 2 meters per second, that might be wrong, because I don't think a rocket's going at 2 meters a second, right? So that's our first equation. Now what we're going to do is, now that we have our second part, we're going to try and find that delta X. So we're going to plug into, so what do we have here? We know our VO is going to equal 300 meters per second. We know our VF is going to equal 0 meters per second, because we're trying to find the top of the parabola. Same thing as the ball example, same thing as the flower pot. When something changes direction, it's going to have velocity is 0 at the top, but it's going to have a constant acceleration, right? So we know our acceleration is going to be negative 9.8, because gravity does not disappear. It'd be kind of kick ass if it does. but it would also suck because then we'd fly into the sun. But so we got an A. And what else does it give us? We want a delta x, and it doesn't give us a time. So that's basically all we need, right? So let's bounce over to our little equations and ooh, everybody's favorite equation: delta x equals VOT plus 1/2 AT squared. Wait, that's not it. I lied. This one, everybody's favorite. V squared equals V initial squared plus 2A delta x. Oh, so exciting. So we're gonna say 0 squared, right? Equals, this is gonna be equation 4. 0 squared equals 300 meters squared plus 2 times negative 9.8 times delta x. So we're going to say negative 300 over negative 2 times 9.8 equals delta x. And then we are going to have to do some more work, sadly, because the way I did this is not entirely optimal, but, you know, that's okay because we're doing it the way that we can do it. So yeah, so 300 divided by 2 divided by 9.8, it's gonna be 15 meters. That's kind of small. Damn, I'm so much better at explaining things than my professor. Well, I'm glad I could help. Okay, we are sadly not out of the rocks yet, right? Because we found this part. We found just 2. But we didn't find the period when it was accelerating. This is just the part where it's slowing down to 0, right? So we now have to go back and find, why can't I be your professor? Well, I can be your professor if you want. I could teach physics, maybe a little bit. If you have any questions, feel free. Like, I will explain them to you. Or like questions about, you know, kinematics or come and teach in Seattle College. I'm not actually that far from Seattle. Well, I am. I'm closer than I was before, but I'm still a little far. So now we're gonna do the last part of the problem, which again, I know this has been a fucking slog, but bear with me. There's probably a quicker way to do this, but this way is the way that like at least makes sense, right? So now we have to say, okay, we need to find the delta x of this portion. So we're just gonna do the exact same thing. We're gonna say, all right, the 300 squared equals 2ax, so 2 times 20, right? Because that was our initial one, times delta x. That seems, oh bro, I forgot the squared on this one. 15 meters is so small. Yeah, it's because I forgot the squared. This is why you check your work. Yeah, yep, that's a lot smarter. Oh my god. 15 meters is like a little bit small for a rocket to go. Yeah, it's because it's actually 400,000 meters. 4,000 meters. Okay, 4,591 meters. 4,592, sorry. And then this one also, 300 divided by 300 squared divided by 2 divided by 20 is going to be 2 equals 2250. And then we add these together, and we do 2250 plus 4592, and we get our final answer, which is 6842 meters. That is the max altitude. Max altitude. It's 6842 meters. Only 9 hours away from North California? Yeah, well, I'm in Central California. Answer is 110 kilometers? Oh, that's wrong. What did we do wrong? Well, first off, this would be 6.8 kilometers, right? That's pretty wrong. That's not like something we can just kind of casually mess up there. Yeah, no, I know how many kilometers there's a meter, don't worry. No, I did not think it was 110 meters. Let's see. Let's do a little look. first off, let's read the problem again, right? Yeah, what's the maximum altitude reached? So the first thing we can always do is recheck our equations, right? Let's see if there's any information. A rocket is fired vertically and ascends with the constant vertical acceleration for 1 minute. It is 1 minute, right? It's not like longer than 1 minute? Okay. Yeah. So let's see. Our initial velocity is... Oh, cute. Let's see. Oh, did they use a different... Oh, wait. So they did... Here's a website with steps. Well, so you can do problems multiple ways, right? There should be no problem doing it this way. Versus another way. I just want to make sure... Oh! I forgot a 0. Wait, I just... Bro, okay, I'm stupid, that's why. Yeah, 20 times 60 is not 300. Why did I think that was 300? How did I pull that out of my ass? That's not 300. Oh my god, that's 1200. Okay, so I think I found where we went wrong. Chat. This should be okay though. 300, bro, 300. That's so funny. Okay. See, the nice thing is the way I went wrong is I multiplied these two numbers wrong. It's the dyslexia. Okay, yeah, 1200 squared. And then, see, it's nice though because when you do a problem like this and you write down all your work, it's actually kind of easy to like go back and check it. So yeah, instead of being 4592, this is gonna be 73469. Wait, that's wrong as well. Hello? That's way worse, right? Yeah, that's like, Let me think. Maybe there are other errors. Maybe there are other errors if there's one error. Let's see, did I get my 2a delta x? That's right. This obviously would not be. Wait, that's 110 kilometers. Wait, never mind. We're right. Let's go, chat. Poggers. I thought it was 11 kilometers for some reason. I was like, bro, that's not right. Let's go, poggers, chat. See, look, that works too. This way works too. Big thumbs up. I would give a thumbs up if you can see my thumbs up, but... So yeah, you can do problems multiple ways. I guess that's the takeaway from today. And this is the way that made sense in my brain. So, you know, you don't need to find the fastest way to do it as long as you can do it. Yeah, total height. This plus 7, 3... Yeah, 109, and if you like round up, 109. Yeah, basically 110. Hell yeah! I'm happy about that. Look at that. We figured out our error even. It wasn't even that bad. Cute. Okay, before I do the other ones, because I know there's other parts to this, I'm gonna do another polar problem because I am streaming in I'm streaming in math. This is physics. As much as I love doing physics, and as much as I will continue doing this, let me do at least one more polar problem because we've only done one and it's been like an hour. Okay. 10. Let's see. It shouldn't take too long though. Oh wait, 10. Bro, what? Okay, fine. R equals 1 minus sine theta. Okay. This is gonna be a cardioid. Here, I'll actually show you the way that my professor taught. So 1 minus sine theta, we know that sine theta is gonna go from 1 to -1, right? So we're gonna flip the sine theta graph and we're gonna shift it up 1. So 1 minus sine theta will have like, we're gonna shift it down 1, I lied. So at 0, sine theta is gonna equal 0, so that's fine. Then at pi over 2, sine theta is gonna, wait. No, I lied, this is gonna be 1. I'm smart. Then sine theta is gonna be 0. Then when sine theta is -1, sine theta is y-axis? Yeah, it is, but it's like 1 minus 0. So like, we have 1 minus pi over 2, right here. Pi. 3 pi over 2. 2 pi, we'll do that. So when it's here, that's 0, right? But 1 minus 0 is 1. Then when it's here, 1 minus 1, 0. Then when it's here, 1 minus 0, it's 1. Then when it's here, that's -1. 1 minus -1 is is 2, positive 2. Then when it's why do I have an extra thing here? That's so weird. Whatever. That's 0 again. So it's gonna look like this. Roughly. And the reason why I'm doing this, you're like, what the hell, Damie? Why are you doing this? Because now when we draw our polar graph, we can just look at this and we can use it as a guide. So we don't have to do all the math out, right? So at 0, we're gonna start at 1. Right here. Then as we go up to pi over 2, we're going to be decreasing, right? So that's here. We'll be decreasing like this. Best I can draw it. Then when we go to pi over here, it's going to go back up to 1. Like this. It's not great. There we go. Symmetrical. Then we're going to go to 2, right? So many trig. It's not that bad though. Like, right? We're just going around sort of like this. We're thinking about it as like kind of like as a clock turning. Let me draw a better 2 here. Like that's like a 2. And then we're gonna decrease back down to 1. And there we go. There's our cardioid. And that wasn't even that painful. Scale is kind of shit, but okay, but now we have to do the area, right? So we know that our area is gonna be from 0 to 2 pi because we just drew this, and we know that it goes from 0 to 2 pi to complete the shape once. You recall this stuff in pre-calc? Yeah. This is a pre-calc thing, but it's also calc 3 thing. Because we talk about like parametrics and stuff, and polar is just a fancy parametric system, right? Because if x equals, r cosine theta, and y equals r sine theta, this is kind of the same thing as these two parameters being related with these two, x and y being related with a parameter theta. It's just a little silly way to do it. It's a very specific parametric way to. Pre-calc's not easy with a lot of different topics. Yeah, that's how Calc 3 is at my school as well. So we're gonna go from 0 to 2 pi, 1/2, r squared, so 1 minus sine theta squared d theta. So we'll do this out, 1 minus 2 sine theta, sine squared theta, plus sine to the 4th theta. Can I explain how to set up parametric equations later? Sure. So some of these are easy, some of these suck. I am not looking forward to doing this. But we'll pull the 1/2 out. So 1/2. We'll do this one 0. This we'll just put it as 2 pi, right? We don't even need to do this. This is just d theta at this point. Calc 4 is a lot of parametric mixed with vectors. Yeah. So if you're interested in that, I can totally tell you how to do that. So 2 times right, sine squared is going to be 1 minus cosine cos 1 minus cos 2 theta over 2. This will cancel, d theta. We can leave the limits in after, and then plus sine to the 4th, which will be 1 minus cos 2 theta over 2 squared, which kind of sucks. I don't actually know if there's a better way to do that, but we're going to do that for this one. Also, let me reset my headphones, because I think that's why the music stopped. If not, I will be sad, but I think it's why. I don't know why. My headphones just suck in their own way, in their own special little way. Oh, we need integration like that in polar topics? Yeah, if you're doing area, then you gotta integrate. Hey, it was my headphones, hell yeah. Okay, we've learned. What was I looking up? Oh, yeah. Yeah, integration like this can happen in polar. Yeah, area inside the curve. Because when you think about polar, in our, you know, in X and Y, we have straight lines like this, right? That kind of define our system. But in polar, we have straight lines out from the origin and curved lines in radius. So when we say area like under the curve, we're really talking about area inside a section, sort of under the curve, right? So it's still area under the curve, but it's more like area contained by the curve. I already forgot how to do them. Area in between two curves. Well, it's not too bad. Like, let's say we had a circle in here. Like, let's say you wanted to do the circle of the area outside this circle, but inside the cardioid. You would just say the area inside the cardioid, right? So just say a card minus a circle, right? It's not too bad. And then you integrate that. Calc 3 seems crazy. It is, but if you, it sucked pretty bad for me when I did it, but bro, my professor is really good. I really like the way he explains things. So I'm happy with it, honestly. I'm glad I took the class. Also, it's not really that bad if you know how to integrate most of the time, if your professor's not an asshole. So this will be minus, right, 0 to 2 pi. This again is 2 pi minus 2 pi. These will go away. And then we'll do another minus here. Minus, right, so cosine of 2 pi, cosine of 4 pi is 1. Minus 0. I've been doing sequences this week. Ah, yes. I don't like sequences. Well, I don't like series and sequences, but... So, the thing about series and sequences is that there is a lot of memorization, but I really like the way my professor talked about it because, so, if you don't know, just a very brief, this was an hour lecture he did, but basically, if you have a crazy, let's say you even have like a curve that's like e to the x or something, right? Like a logarithmic curve. Or exponential curve, sorry. We can, when you zoom in on this curve, like if you zoom in really far, right? You know, we know that like, oh yeah, the derivative here is like is the quote unquote like best linear approximation, right, of this curve. If you zoom in really, really far, right? But if you zoom in really, really far, that this function doesn't become a line, right? It's not a line. So what if instead of using a straight line, we used a curve to approximate it. And since this specific function kind of looks like a parabola, in a way, like a silly parabola, why don't we use a parabola to approximate it at that point? Which would lead us to, you know, f of a, let's say this point is a, plus, if we wanted to write like the line at this curve. So you're just taking these classes to refresh your skill? No, actually, it's one of those things where it's just a prereq that everybody has to take. Like, you can't test into Calc 4. You can, I guess, technically, but what I did was I transferred credits instead of testing into, like, something by taking a test. But I only had high school, I had AP Calculus BC, which covered this stuff, but when you take AP Calculus BC, my school puts you into Calc 3. That's just the way they do it. But we actually covered this stuff. But yeah, I mean, the essence of this is that you take yes, my high school in Hong Kong can't transfer to America either. Oh, that's fucked. See, the essence of this is that you take like a, you know, a parabola at this that goes through this point, or this is the line, right? And then if you want to do a parabola, you do f prime of a, x of a, plus f double prime of a, x over a, over 2, because of this formula that you do. And then you continue this on, and eventually this turns into a series, right? From 0 to n of f of a, f n of a times over n factorial times x minus a to the n, right? And this is the best approximation. And so this is the reason why we want to learn series and sequences in Calc 3, is because, right, when you have something that looks like, you know, 1 plus x squared plus 3x cubed, this is hella easy to take a derivative of and integrate, which is cute as hell for us. When we get into multivariable, we sometimes want to approximate stuff like this because it slaps hard as hell and it's easy for us to do. Approximating functions between polynomials, it's a good idea. You are so right. Dick knew what was good stuff in math, algebraic geometry. So true. Yeah, there are other approximation methods as well. Yeah, and there's a way to calculate how approximate this is through like Lagrangian error, which is something you also talk about. Taylor series is the craziest among all. It like kind of is, but it like also isn't, because they end up just looking like polynomials, right? And we know how to take the derivative of polynomials, and we know how to integrate polynomials. Oh, you have a question? Ah, yes, of course. How do I take exams, online or in person? You misclicked? Oh, no problem. I have in-person exams, but like, I don't know, again, I'm on quarter system, so we have midterms in like 2 weeks. We have it like week 4 of our 10-week quarter, and then we have finals, and then we have another midterm week 8, and then we have finals. I have a quiz in person every Monday, but I have in-person classes, so I just go to class. There are a lot of people in my class though. Okay, so we did this part, right? Now we gotta do this part, which sucks. Oh. Do I plan to study pure math? Not at all, baby. I am a mechanical engineering student. I just do like math, and I like talking about math in a way that I think more people can relate to. Like, I think that math can be... I've met a lot of math majors. It's actually very funny. Streaming on Twitch has got me to meet like at least 6 pure math majors, which is so funny to me and also so cool. I love it. You seem good at a lot of things, like Chinese coding and math. Well, I try. I try a little hard. My brain is like a little silly like that. It's because I just really like learning things. Although I do want to take a class on topology at some point, because I think topology is pretty cool. But I tend to be more annoyed at pure math. I have not learned proofs, and it's kind of kicking me in the ass right now. Or I never really learned how to do like collegiate level proofs, I should say. So it hurts my brain. Rigor in proofs is important. Yeah, that's when I kind of tap out. I'm like, bro. Yeah. Yeah. Now adding more physics into your brain. Physics is, if you think about physics as an application of math, it becomes a little bit simpler. Kinematics is one of the only things that pisses me off, that it's like the first thing you have to learn in physics, because it's one of the only things in physics that doesn't have the main concept of physics, which is, to me, balance. Physics is about offsetting things. You know, Newton's third law, equal and opposite reaction. Every action has an equal and opposite reaction, right? There's pairs of things in nature, right? If I push on a table, the table pushes on me. The moon is currently pulling on me right now, and the earth is currently pulling on me, and I'm pulling on the earth. Like there's you know, a relationship happening. But kinematics doesn't really have that. Kinematics is just like plugging shit into shit, and you're like, why does this happen? Which topic is the hardest in Physics 1? I think rotational motion can be kind of hard. Just because it gets into polar if you work in calculus, and then also rotational motion just can be a little bit unintuitive, because acceleration like points toward the center of the circle, but velocity is tangent to it. So it just, you know, it doesn't really make it as much visual sense. And then Physics 2 is a lot more like that, where you stop getting real world analogies in the same way, and you kind of have to hyper like explode your brain to like ascend to a different plane of like knowledge about stuff. Nowadays, a lot of theoretical physics are interested in heavily advanced math. Yes. It gets more and more abstract and less physically intuitive. I still think that things like magnetism and electricity can be thought about in concrete ways. In the same way that I think like a lot of people think that calculus is not connected to like the physical world. I think it's the most connected. I am very much an applied math little catboy though. I am into making things. I'm into, you know, I like my torques. I like my applications of stuff, my models. I'm actually not even that into modeling, but sure, the classical physics can be more intuitive and say, quantum mechanics stuff and how it can relate to relativity. I think that stuff is fascinating. I did some quantum in the last like stint of my physics last year, and it's a lot. I think it starts to feel somewhat like chemistry to me at that point, because it feels like nuclear physics. Nuclear chemistry. Torque seems hard. Torque itself isn't that bad. Quantum mechanics math is not that hard. But the interpretation, yeah, so true. Torque is like my best friend. I don't know. No, torque is not that bad. It's actually like, to understand torque, all you're saying is like basically a force, right? Applied on a distance, over a distance from a point that's going to turn this. That's all that torque means. The thing about rotational motion is that's a little bit hard to understand, right? If you have, like, let's say you're drifting in a car, and you want to say where the the game over sound, or let's say you're just driving in a circle in a car. That's a little bit easier, right? Here's your car. The velocity is not really that hard to figure out, right? Because you know it's going to be pointed in the direction of the car. And as the car moves around, right, it is tangential to the circle. So that's what we figure out. But what I think it's kind of hard to understand, right, is normally when you have an object that's moving in a direction and you want to say this object is accelerating, this acceleration, right, let's say this is your velocity, in 1D motion or even in 2D motion, right? Let's say this car is moving in 2 dimensions. This is an XY plane, I guess. Or let's say it's on a table. That's maybe a little bit better. Right, your acceleration is going to point in the same direction as that. But when you're accelerating rotationally, your acceleration is actually going to be perpendicular to your velocity. It's going to point towards the center. So I think that can be a little bit hard to understand if your professor, especially if your professor doesn't explain it well. It's one of those things that's just like it's a little bit weird, right? Like you're like, why does that happen? But that's a base level. It's an introduction. I don't want to have to get you too confused about that before you start doing actual forces, because that's not how most forces are going to work. And then when you start doing, like, I think one of the hardest things I've ever studied in physics, and granted this is like a fucking like level 2 year, physics student or whatever, is induced current. And understanding that, like, if you have like a wire, you have like a wire around here and like magnets and shit, like that, like the change in flux stuff, where like, oh, this is like coming like into the page, like out of the page, that is so hard to me. Wait, I gotta go turn on the lights, they just turned off. But that is like so, like, that you can have a positive change in flux and it's going up, and you can also have a positive change in flux if it's like going down. That's hard, I think, to keep track of. But it's very cool, and it's also incredibly useful. Like regen braking uses stuff like this. Engines use stuff like this, like piston engines, like cylinder engines. Let me go turn on the lights real quick. Physics 121 is a computer science wipeout class right now. Yeah, no, I don't really know why they have you taking physics as a computer science student. That's kind of weird. There are people who take math, obviously, because usually you have to take math for computer science. Let me put on some Animal Crossing music. Let's do, like, I don't know, this. Your university requires it. Yeah, I mean, I guess I'm not, like, super surprised. It's just one of those things where it's like, huh, that's a choice that they made. Okay, let's do this last integral real quick so we can be done with it. So let's square this out to my 1 minus 2 cos 2 theta minus cos 2 theta squared over 4. Now this is not awful. It just kind of sucks. Let's write this out again. 1/2 minus 1 plus more integrals, 1 over 4. Am I in a university or community college? I am in a university, which is a T1 university for mechanical engineering specifically. So it's pretty good at being mechanical engineering school. So yeah, it's like nationally ranked, basically. What was I doing? 1/2. Where is this 1/2? Oh, from here. Yeah, California has a ton of good universities. Honestly, I really like the state a lot. And I think that its universities are just like so awesome. Cos 2 theta, cos 4 theta over 2. Berkeley? Yeah, Berkeley is pretty cool. I am not at Berkeley, but it is pretty cool. I did tour there. At some point. Northern California Pacific Coast Highway is the best drive I've ever done in my life. Yeah, there's some really, God, it's so beautiful. Okay, 1/2, -1, plus 1/4, that'll be pi over 2. Nicest beach in America? Oh, true. Spitting facts. Yeah, oh my gosh, I got to see sea lions and sea otters when I came my first week here. It was really awesome. So cosine of 2 pi is gonna be 1. Wait, 4 pi. Oh, wait. I said cosine. I said this was 1. This is 1. Oopsies, this is 0. Go away. Yeah, you used to live in the Bay Area? Yeah. 1/4, 1/2. Oh god, this is so evil. It's 1/2 cosine. Okay, cosine of 4 theta is gonna require a little bit derivation there, but so what's actually gonna stay here? 1/2 pi over 2. 8 pi plus minus pi over 4 plus. Okay, this will be a little bit trickier. We're gonna do this out. So cosine of 4 theta, right? This will be sine of 4 theta over 4. So sine of 4 theta, that'll be 0 at 2 pi. It'll just be 0. This whole thing will be 0, I think. I think it's just 0. I hope it's 0. Wait. At 2 pi, it's 0. And then it's 0 again. Okay, yeah. Thank God. So what is that? That's pi over 8? Is that the whole thing? Did we do it, chat? No income tax in Washington though, which is good. Yeah. Okay, let's see. Let's see if we got this right. Where's this? Let's see if we got the other one right. I didn't even check if we got the other one right. Oh my god, I can't open the file. Oh, there we go. Wait, 7.7. Oh, I wasn't reading. 10.4. Oh, let me turn up this music a little bit for you guys. You can't hear it like at all. Oh, the song was ending. That's why I can't hear it. 5. Wait, 9. Oh no, wait, were we doing 9? Wait, 9 was pi. Okay, we got 9 right. That's good. Wait, it's not gonna tell us the answer to 10. Did I do 10 for no reason? Bruh. They didn't even tell me the answer to 10. I mean, I can... Oh, actually, I can figure it out. Oh, do we dare? Do we dare figure this out, chat? I'm gonna put it into Desmos. Oh, okay, from 0 to 2 pi of 1/2 1 minus sine theta squared d theta. Oh, it's so scary. 4.71. That's not right. Oh, god damn it. Pi over 8's not 4.71. Oh no. I don't even know where to begin where I went wrong. Well, I can copy this and we can check to see if my 1 minus... One sec. 1 minus 2 sine theta plus sine to the 4th. Wait. Oh, sine squared theta. Wait, maybe I actually did get it right. Wait, 1.1 pi over 8? No! Wait, what's pi over 4? No, that's not right either. God damn it, I don't know where I went wrong then. Wait. Oops, I need to put this in a parentheses. Oh, is it not gonna let me do sine to the 4th? Oh, bruh! Too much math has been cramping into your head lately? Oh, I might have to go to office hours and be like, Professor, can you please show me how you did this one? I don't know how to integrate this one. Or I'll just plug it into something else. We can do the other part of that rocket problem, though. You want to repost that? It said something about the time it took, right? To go from someplace to someplace. Maybe, yes, no. Okay. Let's check it, let's check it, let's check it. Well, let's make some space here. Yeah, what is the total time elapsed from takeoff until the rocket strikes the Earth? Ignore the variation. Okay, cool. Ignore the variation of geometry, right? So, going back to our 3-stager here. We'll just say 1, 2, 3. So we know the velocity here is 0. We know the velocity here is 1, 2, 0, 0. And then the velocity here is going to be 0 again. We know this is 1 minute. They tell us that. Oh, there's another. You can kind of say this is 3 and 4. I should add another one here. This is also going to be via 0, but like, so this is the rocket going up. This is the rocket going further up, and then stopping. And then this is the rocket going all the way back down. So, yeah, it's not awful. Let's take a look at our stuff that we've got. So we'll just copy this over. So this is like a equals 20. This whole bit is going to be a equals negative 9.8, right, for all of this. What else have we got? So we need to find this. We know this delta x, right? We found that. Sometimes it's good if you do extra work in kinematics problems and it's a multi-part problem, you can use that in another stage, right? So like, for example, this 36,000, we can use now. We can use the 73469. So this is going to be delta x equals 73469, and this is going to be our delta x is, 110 km. It sucks if you got the first part wrong, then you can't do the rest of them. That is very true, but I will also say, if you show your work correctly, and let's say you get like one number wrong, most professors will not be mad at you like as much. They'll give you partial credit. A lot of the times if you like continually use the wrong number but in the right way. Because really, they can't take off like all, well, I mean, they could, but a lot of people who do multi-part problems won't take off like continuous added points for getting that number wrong. They'll take it off in the first place you got the number wrong, but then like not for the rest of it. I'm so mad that this pi over 8 is wrong. That's fine. That's fine. That's fine. Take a stretch out. Okay. So yeah, I think we have everything we need now, right? Now we just gotta like pick out which equation we kind of find is like kind of vibing with us. It's nice that I have this on a layer. I should just have this everywhere. Where did it go? There we go. It goes right there. So yeah, which one do we want to do? I'm kind of feeling the delta v equals. So for this topic, we just need to know velocity, acceleration, and distance. Yep, that's pretty much it. The only thing you might need to do is, for example, let's say you're given a equals 3v squared dt. If you're given a equals 3v squared or something, you do potentially, if your class is calculus-based, if it's physics 121, maybe it isn't calculus-based, but you do have to know how to say, okay, a equals dv dt equals 3v squared, 1 over 3v squared dv equals dt, ln of, yeah, you need to know some derivative. I should just say 3v squared to the negative 2. I hate doing that. Then you need to just say like 3, v1 over negative 2 plus c equals t. Yeah, that's pretty much it for this topic that you would potentially need to know. So I'm just gonna go with 1. I mean, I think we're gonna use equation 1 for this one. Delta V equals AT. So that'll be 12, negative 1200 equals negative 9.8 T. T equals, what do we got for T? 122.45 seconds. And then for the second one, we don't really want to use it like this because our V's are both 0, so that wouldn't really work. Just kind of because the zeros would cancel out. But we can use, I think I would use 3 for this one, so we know it's 110 kilometers equals 0 plus 1/2 negative 9.8 T. Well, sorry, that'll be negative kilometers, right? Because it's a displacement. And then that would be, you know, see, 110 times 1,000, because we got to make sure it's in meters, times 2, divided by 9.8, which is, did I miss something? T squared. So 22448 equals T squared. And then this, like, can I just square root that? History equals T equals. So displacement is always negative. No. In this case, right, when we're looking at this, we know that the rocket is starting up here and it's falling down, right? It's going down. So that's why our displacement is negative. So we just add all these up, and then that's like 60 seconds plus, you know, roughly, we say 1 minute plus roughly 2 minutes plus another roughly 2 minutes. It should be like maybe 6-ish minutes. Maybe? So like 360 seconds-ish? Hey, that's pretty close. Yeah, 330. I mean, if I do it out, I bet I can, well, we can see what happens if we do it out. So 140 something, right? That's what we just calculated. Plus 122.45 plus, oops, not 9, 60. Yeah, 332. So that's close enough to, like, and we can say like T all or something equals 332 point, you know, 3 seconds. Beautiful. They might have only asked for 2 sig figs, which is why they might have rounded. Although I don't really know anyone who asks for 2. Lots of people ask for 3 sig figs, but look at that, perfect. Boggers. Now, if we had gotten this wrong and we said like this was, you know, 300, my small brain, they most likely would not have taken points off for you getting the 300 part wrong. They probably generally would have taken stuff off, but if you had done the work, like if you had used these equations and like shown that you can use these to get the thing, they would have given you probably at least like a 80% credit. How did I get 320? Oh, I just added this time, right, which is the one that we found for this, and then this time, which is the one we found for this, and then this one, which is the one that they gave us, which is 60 seconds, right? It equals 60 seconds. I just added up the 3 times for the 3 different sections, which again is the part where the rocket's accelerating upwards, the part where the rocket's slowing down, and then the part where the rocket falls back down and is accelerating downward, right? Yeah, the 60 seconds was what they gave us from the problem. You could also calculate it out because we have enough stuff to calculate it out, but I'm lazy, so I'm not going to calculate it out. Yeah, you know what I actually could do is let's do a setup for a polar real quick. Hopefully one that has an answer this time. Me not fucking choosing one with an answer. That was stupid. I can't believe I chose one that was a even number. God damn it. Okay, 17. Let's do one that has a proper... Jesus Christ. Okay, 17. Find the area of the region enclosed by one loop of the curve. Ah. So R equals 4 cosine 3 theta. Do I have time to do parametrics? Yeah, sure. If you have an example of parametrics, then totally hit me up with it. Like, do you want me to show you how to turn it into a non-parametric equation? I don't really... There are a lot of things you can do with parametrics. Like, do you want me to show you, like, the area, like, the length of parametrics? Oh. Okay, actually, yeah, we can do that with x and y, right? So, like, let's do x equals r cosine theta, and y equals r sine theta. Well, okay, sure, yeah, you can post one to Discord. Let me see where that is. Do I have that? Oh, maybe not. Maybe I do. I don't think I do. You can also do it with the parametrics, the polar equations. Okay, I'm gonna get a little bit started on this though. So we want to find one leaf, right? So I think drawing this out is gonna be the easiest way to do this. So first off, that means there's 3 iterations of, there's 3, like, what is it called? What is it called when it does it? It's called a curve that starts with a P, it repeats, it's a repeating curve. Yeah, we're gonna go with that one. So when it equals 0, it's gonna equal, when theta equals 0, it's gonna equal 4, right? Because it's cosine. But when, normally at pi over 2, this is gonna be theta x equals pi over 2. Wait, 3 theta equals pi over 2, I lied. Theta is going to equal pi over 6 instead. So we have pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, etc. 5 pi over 6. And then it goes on for a very long time. I'm just going to do 6, 7, 8, 7, 8, 9, 10, 11, 12, right? That's for 12. So at this, it's going to be pi over 2, which is 0. Then it's going to go down here to -4. Right, then up, and then down, and then up, and then, okay. So what we can do, the easiest leaf to find is going to be from pi over 6 to 3 pi over 6, because that's a full leaf that's being drawn in that time. Okay, let's see. This is... Oh. This is not a parametric equation. Is it a parametric equation? Ooh, Oh, this is just a line in 3 dimensions, I think. I mean, we can look at it. I can write it as a... Okay, let's... Do I know how to write this? Whoops. Okay, so I guess the first part of what we would think about is just figuring out what this second point is, right? So we know that, yeah, this guy wrote it here, 003, but it's going to go over 4 in the positive x direction. So first it's, going to go over 4 this way, and then it's going to go 7 this way. So the way that I would write that is 4, 7, 3. So we're going from 0, this to this. Now writing an equation for its line of flight is kind of strange. Let me just look up one real quick thing, because we could do point slope formula. But do I know how to do that in 3 dimensions? Point slope in 3D. I don't know if I'm well equipped enough to explain this. Oh, you have to represent it as a pair. Yeah, I haven't done this before. I can see how it's done, but I would not be able to explain this because I have not done this before. In this way, I suppose. Which is a sage moment. Yeah, I know. Sadly, yeah. I mean, I can if you like said like, oh, how do I get rid of something in a oh, is it Calc 4? No, I think it's just like the second half of my class. I just haven't done it yet. Or it might be my physics class even, because we do 3D stuff in physics. Anyway, from pi over 6 to 3 pi over 6, we're gonna do 1/2 r squared, which is 4 cos 3 theta squared d theta, which is so cute that this is so easy. Okay, so we're gonna pull everything out to the front, right? 16 over 2, that's 8. And I'm not gonna really worry about the limits right now. Parametric equations is easy to set it up. Well, depending on the problem, I mean, it's not that bad, I guess I would say. Like, you normally just have x equals, like, I don't know, like let's say, like, t squared plus 1, and then y equals, like, 5t plus 6t squared plus 3. I don't know, and then you just solve for t, basically, and then you get an xy equation. But I just don't know it in context, so I don't know how hard or easy it would be to set up. I assume it's not too bad, but, you know, then again, I can't really speak from experience or anything. Okay, so we're gonna do this real quick. This will be 8. 1 plus cosine of 6 theta. Oh, the last cross product problem? Okay, I also am technically not really super equipped. But one way that you can think about it, which is kind of gonna be hard for me to explain. Okay, let's do it like this. So let's say you have vector A cross vector B. One way that you can think about it is this is one of the problems that's sometimes coined like a right-hand problem in physics, at least in the physics sense. We're not talking about in math, not cross products in math. Because what you can do is you can think about the vectors with your right hand. So if you take the first vector and you use your pointer finger to represent that vector, right? So this is your pointer finger. This is going to be vector A. And then your middle finger to represent vector B. Your other two fingers are not doing anything. Then your thumb will be facing up. So the mother vector is the normal vector. The mother finger is the normal vector. I'm not sure exactly what you mean by normal. Then your thumb will be AXB. Yes. So like, let's say you had, let's do like another example. Let's say you had let's say this is a table, right? Let's say you have vector A over here and vector B pointing into the table. Then you would point your finger, right, towards vector A, and you would point your middle finger into the table, and your thumb would be pointing to the left. Do you see how that works? I don't know if you're doing it with me, but I assume you are. That means that your cross product would be pointing to the left. This is AXB. And a bird's eye view of this would look like this. This is a bird's eye view. B is going into the table. We can't see it. This is AXB. That's one of the ways you can think about it. It kind of starts to fall apart when you have three-dimensional space. But in physics, a lot of the time I think you're going to be having... How can we find the vector component? Okay, so the question that problem was asking was kind of a specific question, and the only way that I can think about this without like doing just matrix math is because, so for the first part is like figuring out where the cross product is, right? You know, if you have two vectors, what they're kind of saying is you have two vectors in space on the same plane. So we know that the cross product either has to be up or down, like pointing, it's going to be something on the z-axis, right? And I guess we technically don't really know which way it is on the z-axis. But like conceptually, we can think about this with the right-hand rule as it's got to be on the z-axis, right? So what you can do is you can take that value, right? 9 times 13 times sine 30, which is like what is it? It's like 4, or so, I don't know. It's not 4. It's not, what's 9 times 13? Like 90, and then like times like half, like 45-ish? Maybe more than 45? Whatever number it is. So you know that it has to be like the I component and the j component have to be 0. And that's going to be the k value. And because it's not sine of negative 30, then it's positive. That's the best explanation I can give you. Because if it was in 3D space, I don't think you could do it like that. Okay, sorry. It is in 3D space. If it was like kind of tilted or something, like if those vectors had like their own components. Can you explain why I and j is 0? Okay, yes, I can. So one of the things about cross products that I like to think about is you have 3 vectors, essentially, right? You have 2 that you're cross-producting, and you have 1 that's going to be the resultant. And those 3 are all going to be perpendicular to each other. So you're going to end up with something that occupies all 3 planes. If you are working with your vectors on one of the planes x, y, or z, all right, x, y, this is our x, x, y, and z, right? In one direction. There's going to be a vector that occupies each of those planes, if that makes any sense. That might not be a great way of saying it, actually. That works a little bit better in physics applications. Because the 2 are on a flat plane, the other vector is going to be pointing up and down. Does that make more sense? And you can think about it with the right-hand rule. Although that's kind of just like this is more of like a technique thing than it is like something that you should always think about. What about the dot product? Okay, so the dot product is a little bit different, right? Because the dot product is like a number. The dot product is sort of like when we multiply 2 scalars. Like if this was just like like if a equals 5 and b equals 3, ab equals 15. In the same way, if you have a vector like a equals 5, 3, and b equals 6, 7, your dot product is just a number. It's 5 times 3 plus, or 5 times 6 plus 3 times 7. So that's just a scalar, like, property of 2 vectors. It doesn't really exist in a 3D space, I guess. It's mostly used as something to... Is there a specific location of a dot product in a diagram? As far as I know, no. But a dot product is used in a cross product, I'm pretty sure. So don't quote me on that. I don't know if that's true. I think it is. I'm not really super equipped to deal with like three-dimensional vector applications in physics. I will be like in a couple weeks though, probably. So if you're interested then, you know, feel free to ask if you're still confused. Do you hate vectors? Oh, well, vectors are a little scary. I will say that. They can be a little bit mean, but they're really not that bad all the time. You know, if you kind of work with them, if you meet them in the middle, then they're not too scary. In the same way that I think a lot of math is. If you view it in a certain light, it can be very, very overwhelming. Lots of crazy parametrics just mixed with vector plane. Yeah, I haven't done that yet. That's my, like, probably my week 6, maybe? I'm coming into week 3 of classes, so. But anyway, let's just, like, finish this up, and then I'm probably gonna call it soon. What is my last week topic? I actually don't know. It's basically like we're gonna be moving into multivariable, so we might be talking about like gridding or something, or potentially partials, if I had to guess. You had to learn polar in the last week. We learned polar first, which makes sense. No, we learned parametrics, then polar, because polar is just a type of parametric. And then we briefly went over Taylor, then we're doing series and sequences, and then partial derivatives. Yeah, they might have us do partials. They're really not that hard. I mean, like if you have like x squared plus y squared, and you said like, you know, I forget what the symbol is, but it's like, you know, I think this is it, right? Like partial with respect to like x, then that would just be like 2x plus 0. Like it's just a constant, you know. Calc 3 is supposed to start with series and sequences? I don't know. I think that like Calc 3 is basically the unwanted child of the math world, sadly. I think that if I was a professor, yes, conic, there's also conic. We're doing conic in one of the weeks. Like if I was a professor and somebody said teach Calc 3 and I hadn't had my current professor, I'd be like, damn, this like is the worst calc to teach. Because like derivatives, yeah, you have a problem you're solving for the whole quarter, right? Like you're solving like, what's the slope? Instantaneous slope. Integrals, you have a problem you're solving for the whole quarter. What's the area under the curve? But then Calc 3 is like, well, here's a bunch of shit you need for Calc 4. But it doesn't connect at all. And like, it's kind of like the physics 2. It's kind of like the AP physics 2, which was, we're going to teach you fluids and thermo and electrostatics and magnetism and quantum physics all in 1 year. But not a lot of any of those things, just a little bit of all of them. It's just funny to me. So, okay. This will be 4 times 2 times 3 pi over 6 times 2 pi over 6. Oh. Plus 1/2 times sine of 6 over 6. And then we'll do this little switcheroo here. 2, 3, 4 pi over 3 plus 1/2 times, oh, this is gonna be kind of annoying. Am I planning to ace them this quarter? Well, I'd like to, you know, that'd be like kind of cool. Do I think I'm gonna ace everything? Probably not. I will say, one of the things that my professors love to say for mechanical engineering is that people come in with an average GPA of 4.3, and then they get an average GPA of 3.4 for the first quarter. So I'm really not like, I'm not gonna beat myself up if I don't. I mostly want to like understand the concepts and like do well in class and stuff. And try to like learn, you know, because that's what really matters to me. But, you know, it'd be a bonus if I could get like some A's. You have a CS class with a B? That is A-okay. C's get degrees, babe. It's costing you a lot of GPA. Yeah, if you're planning on going to like grad school or something, then it matters a lot, I know, but... Oh, I can pull out this 6, so this can be over 12. Ugh, 112, gross. Okay, so sine of 3 pi over 6 is going to be sine of 3 pi, which is going to be a big fat 0 minus sine of pi, which is going to be another big fat 0. Okay, 4 pi over 3. If this is wrong, I am going to cry a little bit, but not a lot. 4 pi over 3? Fuck, what was this, 11? 11 pi, bro, what the hell? Wait, no, 17. Oh, it's like gambling. 4 pi over 3, let's go, baby, let's go! Sorry, that was probably really loud. Oh, poggers. A lot of people cheat when the exam is online. Yeah, people cheat on everything, but if you don't cheat, then you learn, and that's what's really important. I could just not do any of this work for this class. None of this is assigned work, but I want to do it because it's fun and I enjoy doing it, and also it makes me better at stuff, you know? Just like how I don't have to do other people's math problems to explain them to them, but it helps me learn better and it helps you learn better, and it's fun. And also, it makes me better at things. With that beautiful win, with that beautiful dub under my belt, I think I might turn in for the night. I think it was a very good, not very productive. We did only do technically 3 of my problems, but we had a good time. We met some new people. ABC Conjecture, who is probably not here anymore, but that's fine. I don't really mind. They were nice to have around when they were here. I hope everybody has a lovely, lovely night and a good day and a good time period, whatever, I don't know. And yeah, I hope you experience the highs of solving a physics problem or a math problem for like an hour and then getting the right answer and not having to like check your work at all. Waking up for 9 a.m. Waking up at 9 a.m. tomorrow for lecture physics. I am with you, bud. I have 9 a.m. or I have a 10 a.m. class, so I have to wake up at like 9 or earlier. It's communications, though. I have to practice my speech. Probably not understanding anything? Well, if you have questions, feel free to ask. I would record my my physics lectures. If you actually have like some problems understanding stuff, though, Khan Academy has some great physics resources if you want to watch videos. Yeah, I have to take a communications class. That is required of me. It sucks. I actually should probably practice my speech tonight. Ooh, I don't have to do it tomorrow, though. I have to do it in 3 days, which is on my birthday. So, you know, not really too hyped about that, but doing what I can, so. But yeah, hope everybody has a great night. I will be back on Tuesday. CMST 210? No, it's Comms 101, actually, called here. But, yeah, it sucks. Sorry. My professor's not watching this, I can say it sucks. Yeah, it fucking sucks. Yeah, it's not like I Twitch stream for like 2 hours every day. Like, that can't get me out of comms. It's not like I present physics problems or anything. It's not like I publicly speak to people. It is boring as hell. It's kind of important, but also the way that it's taught is like not important at all. It makes it kind of like negates the point of taking a comms class, in my opinion, but you know what? Not much I can do about that. It is a graduation requirement. So I hope everybody has a great night, good sleep, good day tomorrow, good week, whatever. And I will see y'all next time. Bye! I would wave if I could, but I can't. I should make a waving animation, actually. Bye!